It's my pleasure to introduce Amzi Jeffs from University of Washington. And Amzi will be telling us about how we can arrange sunflowers of convex open sets.
Cool, yeah, thank you for the introduction and for having me. Yeah, feel free to interrupt during this talk if y'all have any questions or anything. I'll try and at least keep an eye on the chat, but interrupt verbally as well. Yeah, so I'll start off just by giving kind of a broad overview. The main quantity that I'm going to be interested in is something called open embedding dimension. I'll tell you what that is. But I want to start off with just a very bird's eye view. And if you've seen one of my talks before, you've seen the slide, so apologies, but I think it's a good place to start. The kind of vague question we're trying to answer is how we can arrange convex sets in d-dimensional space in general. And in particular, how can they intersect and cover one another? That's sort of what I mean by arrange. And yes, similar to Caitlin's talk, there is some biology motivation for this. Neuroscience, if you want to look it up, the thing to Google would be place cells. I won't talk about it too much. I'll just say that, yeah, as Caitlin mentioned, there are certain neurons in the brains of at least rats is where they're studied the most, but that's generally a good model for mammals. And those neurons are active in a convex, roughly anyways, convex region in the animal's environment. So we're interested in how all those regions where different neurons are active can play with each other and how that looks then in the neural activity, and how much structure of the space, this sort of way of mapping the space can capture. But of course, this is a combinatorics conference as well, and I think there's plenty of mathematical motivation coming from discrete geometry and topological combinatorics and so on. If you look at Helly-type theorems, nerve complexes, polytopes, hyperplane arrangements, those all kind of fit in this broad umbrella. And this paper I've linked at the bottom is actually a nice survey from 2011 of this particular topic I'm talking about, or at least an older version of it. Okay, so let me make that vague question a bit more formal. We'll need some combinatorial objects to record information. I'm going to use codes, which are really very arbitrary. They're just any subset of the power set on 1 through n. Yeah, it's an artifact of the neuroscience motivation, but I will sometimes call the indices between 1 and n neurons. If I ever say that, I just mean a number between 1 and n, nothing fancy. And then the elements of a code I'll call code words. So here's a code we can look at. Here I've got 3 neurons, 1, 2, and 3, 6 code words. You'll notice I'm making my notation a little more compact. This is, not 123, it's 1, 2, 3. Okay. I've got the empty set as a code word and so on. So those are my combinatorial objects. On the geometry side, I'm going to use collections of convex, in particular open sets. I won't have time to talk too much about the fact that I'm using the word open here, but it is important. You'll have to trust me. And I'm only going to think about open sets during this talk. And what I want to do is, yeah, again, record how these intersect and cover each other. So if I have such a collection, let me just wander around all of RD. At each point, I'll label that point corresponding to which sets the point lies in, collect all the labels I get that way, and then I have some code on n neurons because I have n sets. And I'll call this collection of sets a realization of the resulting code. And I think a picture makes this a lot more clear. Here I've got the same code from the previous slide. I have a realization of it in the plane with these 3 ovals, which are, yeah, indeed convex open sets. And for example, the code word 2, 3 comes from this gray region where I'm in set 2 and 3, but I'm not in set 1. And likewise, the singleton 3 comes from this right-hand piece where I'm only in set 3, etc. And I want to give myself a little structure to think about this question of how I can draw these realizations. So the quantity I'm going to use is called open embedding dimension. This is just if you hand me a code, what realizations can I find? What's the smallest dimension I can find a realization using convex open sets in? And maybe I can't find one, in which case I'll say just by convention, this number is going to be infinity. And yeah, let's look at this example that I had on the previous slide again. So here I had a realization in R2. So I know the open embedding dimension is no more than 2, but actually I could squash all my sets into intervals, get the same code. So really the open embedding dimension is 1. And here's a code that looks really similar. It's still 3 neurons. I've got 5 code words. And it turns out this one I can do in R2 with the following picture. I have these 3 kind of flaps that meet in a square. In this square, I get the code word 1, 2, 3, where all the sets meet. Outside, I get 1, 2, and 3 as singletons, and then the empty code word. And I can't flatten this one because I kind of need this second dimension to extend a piece off. So here the open embedding dimension is 2. And then let me just convince you that I need this convention that things can be infinity. Here's a code, again, 3 neurons, pretty simple, but only 3 code words this time. And what you'll notice in this code is that neuron 2 always appears with 1 or 3, but never both of those at the same time. So if I tried to draw a picture of this, I'd have U2 covered by U1 and U3, but those are disjoint. And that's not even possible for connected open sets, much less convex open sets. So here the open embedding dimension is infinity. Okay, so those are a few examples. And yeah, this is the kind of big picture we're looking at. We have collections of convex open sets. We know how to turn them into codes pretty quickly and easily. And I want to be able to go the other direction, in particular, in a sort of minimal way where I find a realization in a small dimension. And that's the general question I'm trying to answer is, if you hand me a code, what can I say about its open embedding dimension? And I'll just advertise that this is a relatively recent question. There's a citation for the paper that first raised this in 2013, again, motivated by these place cells. And of course, this has ties to much older ideas in discrete geometry, but even in just the last, I guess, what's it been now, 8 years since it was first posed, there's been a lot of interesting kind of math that this question is motivated. And I'll tell you a little bit about some of that today. Any questions before I jump into maybe the meat of what we can say about this? Okay, great. Yeah, so I'm interested in sunflowers of convex open sets. In a couple slides, I'll tell you what a sunflower is. But I wanted to start off with kind of the first example that these showed up as in the literature. So this is from a 2015 paper published in 2017. And the situation we'll look at is that we have 3 convex open sets in the plane. And they're similar to this picture I showed you earlier, where they all meet in a central place. They all intersect. That's the code word 1, 2, 3. And then outside of that place, I only have 1, 2, and 3 by themselves. And what you can say about an arrangement like this is if you try and draw a line through each of these sets separately, you actually have to draw that line through the place they all meet. You can't sort of slice through the sets without going through the intersection of all of them. And I'll sketch for you sort of why this is true very, very informally. Let's assume we could, slice through these sets without going through the region where they all meet. And that's this left blob over here. And here's my line. It goes through points P1, P2, and P3, and U1, U2, and U3, respectively. And a convexity I can actually reduce to the case where I've slid this line right up to the edge of the place where all these sets meet. And now let's look at this green region. So P3 is in U3, as is this entire blob. So this convex hull here must be as well. All this green stuff is in U3. Same trick with P2 and U2. But now I have a problem because I have a place where U2 and U3 overlap, but it's not in this blob, right? So this will give me the code word 2, 3, which I know I don't have. So this is a problem. Of course, you have to do some more casework, and I think the original proof is kind of different than what I'm showing you here, but this gives you an idea of the kind of issue you're running into. And I'll just say that, so there's a few consequences of this result, but one consequence that I'll state in this talk anyways is that there's a certain code S3, and this theorem tells you the open embedding dimension is not 2. It has to be at least 3. It turns out that it's equal to 3. So what is this code saying? So I have, in this case, 4 neurons. The first 3 are behaving like that arrangement on the previous slide. They all meet. They don't meet outside of the place where they all meet. I only see 1 at a time outside of that place. And then the 4th neuron kind of slices through all of these, but it doesn't hit that 1, 2, 3 place. And so here's a picture of how this would look in R3. I have my 1, 2, and 3 sets coming off at perpendicular angles. And then I have this 4th set that kind of slices through all of them. And I really can't draw something like this in R2. So I have a code version of this theorem from the previous slide. And what I want to do is kind of generalize that situation. So the arrangements I'm going to look at are going to, just be very similar, but I'm going to have more sets in them. And I'm going to call a collection of convex open sets a sunflower if I have the code word 1 through n, so all the sets meet, and then I only have singleton code words besides that, plus the empty code word. And I'll call the sets in a collection like this petals. I'll call the region they all meet the center. So here's an example like we've already seen. I have 3 petals My center is this kind of shaven circle thing, and this is in the plane. Here I have 5 petals in R3. Here I have 4 petals in R3. Here the center is this triangular prism. Here it's a cube, and the 4th petal kind of comes off the back diagonal of it. Okay, so these are the objects I'm kind of interested in looking at. And what can we say? So there was something in this previous result where I sliced through all the petals and I had to hit the center. So here's a sort of different way to phrase that. If I have, let's say, enough petals, and I choose 1 point from each petal and take the convex hulls, take the convex hull of all those points, I have to hit the center of my sunflower. And what is enough petals? Well, it's dimension plus 1 of whatever space I'm in. And I'll just say the proof of this that appeared in 2018 was very nasty. I wouldn't recommend reading it. There's, by contradiction, induction on the dimension, all sorts of nasty sliding things around type of arguments. And at that time, actually, Z. Rosen had a better idea, another researcher in this field, and suggested it to me, and I didn't see how to make it work, but I'll maybe at the end of this talk gesture towards how we would have used that and actually in a more general setting. But let's just use this theorem and see that it works. So in all these examples I drew you, I have at least as many petals as dimension plus 1, so 3, 5, and 4. And let's choose some points from each petal for each of these sunflowers. And let's look at their convex hulls. And here we see indeed, this triangle overlaps the center here, doesn't cover it, but it does intersect it. Likewise, this tetrahedron over here intersects the cube that is the center of this sunflower, and so on. Okay, so this is a nice theorem that tells us about how these arrangements that are sunflowers are behaving. And it turns out we have a code kind of version of this as well. There's a whole family of codes. So I showed you S3. You can make an SN code that kind of tells you about, that describes an N petal sunflower with another set that slices through all the petals without hitting the center. And this theorem is telling us that the open embedding dimension of that family is exactly N. So these two theorems on this slide are phrased very, very differently, but they are basically equivalent. So somehow this geometry result is getting at open embedding dimension, which I was interested in. Okay, so in the final couple minutes of my talk, I'm going to take us just one step further. So we had sunflowers. I'm going to weaken my condition on them a little bit. I'm going to still be stipulating that the petals all intersect somewhere. But then I'm going to allow them to be kind of flexible and overlap each other outside that center, but no more than K sets at a time. So I'll call a K flexible sunflower a collection where I have, again, they all intersect, but then the rest of the code words have size no more than K. And here's an example with now I have 5 petals and I'm in the plane, and now K is equal to 2. And here my center is this square, but outside of that square, I can have some overlap, but only 2 sets at once. So here these 2 sets overlap outside the center. And we're going to get, it feels like, I think, a pretty natural generalization of the previous theorem I showed you. As long as I have enough petals and I take a point from each petal and take the convex hull, again, I just have to hit the center of my sunflower. And before, what was enough petals? It was dimension plus 1. Now it's dimension times this parameter K plus 1. So I've introduced a new parameter to sort of loosen things up, and all it's really done is multiply the number of petals I need. And let's look at this example that I already showed you. So here again, it's a 2 flexible sunflower in R2 with 5 petals. So 5 is larger than 2 times 2. And indeed, if I choose 1 point from each petal and take the convex hull, that has to hit in this case, the square that's the center of my sunflower. Okay, so this is kind of the most general version. And I think what I want to gesture towards, I won't really get into the full details, is the proof. The reason I want to say this is, this is, again, this idea that Zvi had about how to approach this and apply some nice old-fashioned discrete geometry results. So what would we want to do? Let's work by contradiction. In this case, I'm drawing you a very sketchy picture with dimension 3, K is equal to 2, and I have 7 petals. So here 7 is larger than 2 times 3. The theorem should apply, but what if it didn't? And I could choose these points whose convex hull didn't hit the center. Okay, well, let's stick a separating hyperplane, in this case, just a plane between these 2 sets. let's project all of these points onto that plane. And the way I've cooked things up, I have exactly the right number of points to apply something called Tverbreg's theorem. And actually in the k=1 case, which is what Zvi was talking about, this is going to be Redon's theorem. I can partition my points in a nice way so that the parts, the convex hulls of all the parts, share some common point. And the final piece you have to argue is just that this point, by virtue of being in all these partitions, should be close to the center. But the way I've cooked it up, it's actually positive distance away. And so that's the kind of contradiction we get. And so, yeah, I think that's, the reason I wanted to highlight this is because I think it's a nice application of Tverbreg's theorem. And I think I will end there and just say that, we had a nice code version of the previous theorem with k=1. We don't have a nice code version here. We have some bounds, but not exact numbers. There's some open work to be done tightening that. And also just wanted to give this talk to kind of advertise this theorem. If you ever see convex sets that are all meeting in a central region, maybe you can apply something like this and say something about the structure of those. Thanks.
Let's thank the speaker. A very nice talk. Do people have questions for Amzi?
I have a question. So let's say you have like a bunch of petals in like a small dimension, like, I don't know, 8 petals, or like just like 4 petals in R2.
Mm-hmm.
Just like sketching in my notebook, like during your talk, I feel like, so in R3, you can have like with 3 petals in R2,
mm-hmm.
you can have like for every pair of petals, you can take points in the convex hull and one go through the center.
Yeah.
I kind of feel like in R3, with 4 petals in R2, there's got to be like 2 pairs, there's got to be a pair that goes to the center.
You need pieces that go in the opposite directions. Yeah.
I don't know, have you thought about the case of like, how many of the smaller subsets can like not go through the center?
Yeah, it's a good question. I haven't thought about it too systematically, but I think it's definitely like a pretty natural thing to ask about and would give you maybe more families of codes to investigate or like say things about the dimension. I guess one thing you could do is you could say like, let's say we have a k-flexible sunflower, and let's take subsets of the petals where I can choose points and convex hulls don't hit the center. Then the sets of petals that satisfy that would form a simplicial complex, because you can always delete points from the convex hull. So maybe you can say something about that complex being, certainly, I guess my theorem tells you its dimension can't be too large, but maybe what you're saying is that it also has to have a certain number of faces of other dimensions.
Yeah, I don't know what the result is, but I hadn't thought about it before.
Yeah, me neither, but I think you could say something. I suspect at the very least you're correct that if you have 4 petals in R2, at least 2 of them should not be able to like see each other. Yeah.
So you're dealing here with convex open sets, and if you remove the convex assumption, this becomes like vastly different problem.
Yeah.
Is switching from like open to closed or dropping open entirely, does that dramatically change this problem?
Yeah, actually, unfortunately.
Okay.
Actually, not unfortunately. I like that it doesn't, or I like that it changes it just because it means like there's something interesting about open sets that doesn't happen for closed sets. There's like a weird distinction somehow. But yeah, the way it would change it, maybe I can even annotate here. If I wanted sunflowers of closed sets, this theorem becomes like trivial or just not true even in R2, no matter how many petals you have, because I can always just take line segments meeting at a point and then slice through them all with a line, as many line segments as I want. And so, yeah, this shows you that the theorem really, like open sets is a extremely important part of the assumption. Yeah.
Thank you.
Any more questions? All right, let's thank the speaker again.
Thanks for having me.
They're both really great talks. Thank you both.